Hello, folks. This video is an optional final bonus topic that I've added to this course. It wasn't listed as part of the syllabus. It's about machine learning for relational DBMSs. It's an emerging hot area of research, and there's a lot of interest in industry as well, so I just thought I should include this. As with topic 8, the other big data systems, this one is also not included for your final exam. Okay, so this is only if you're interested, you can have a look at this. So the first question is, why should we bother applying machine learning to systems issues that are well studied and understood over the course of several decades? We saw a lot of issues spanning the entire stack of a relational DBMS, right from storage and buffer management through indexing and sorting to operator implementations to query optimization, transaction management, concurrency control, parallel RDBMSs, and so on. So now the question now becomes, where can ML help and why should we even bother? The best answer for this is given by Jeff Dean of Google again. So if you recollect, Jeff Dean of Google File System and MapReduce Hadoop fame, he also led the implementation of TensorFlow. So he gave this wonderful keynote at this workshop at the NIPS conference, which is now renamed NERPS. He says, handcrafted heuristics are pervasive in systems, but these handcrafted heuristics are not adapted. They're not tailored towards the distributions of the data that these systems see. And so he says data-driven machine learning can help improve metrics for these systems, metrics like throughput, latency, storage footprint, all of that, and costs. There are also various user-tunable knobs and configuration parameters that have exploded in many of these real-world systems. Take, for example, relational DBMSs, industrial strength relational DBMSs ship with at least a few dozen knobs. All these knobs range from how much memory to give for a sort operator, how much memory to give for a hash operator, to degree of parallelism, and so on. And they're very painful for a user to tune. Okay, so a lot of database administrators, their job revolves around tuning these knobs. And so Jeff Dean says machine learning can be helpful here. There's also computation hardware that has evolved. We're no longer just in the realm of CPUs. We have GPUs, we have FPGAs, we have accelerators. And a lot of these devices are now available over the cloud. And so resources costs have become lower. And so the question is, can we exploit some of these modern hardware to reduce latency? And last thing is machine learning algorithmics has also evolved. Automated ML procedures, auto ML heuristics that I mentioned in the last topic are also enabling ML to be used by system developers. Okay, so then system developers do not need a PhD in ML to understand how to use ML for systems. Okay, so it's a perfect storm of all these issues. Technically, we could have used machine learning for systems even 2 decades ago with simple machine learning methods. But these days, it seems like the availability of more advanced ML tools and resource capabilities and the explosion in the complexity of modern computer systems has led to the reconsideration of using ML for systems. Now, of course, people have been studying ML for systems for almost 2 decades or more now, since the early 2000s. There's a lot of work in the database community on what are called autonomous database systems that have been going on for a long time. Now it seems like the wider systems community has woken up and understood that ML can help systems as well. One other cynical reason, if you want to be cynical, is it's a controversial topic. In many of these systems communities, there's polarization. A lot of people saying ML used in this context is not principled. It's too heuristic, it's too ad hoc, it's brittle, it might fail, it's not reliable. Whereas more principled algorithmic approaches that have theoretical backing, where we understand the behavior in a fine-grained manner, might be safer, might be better. But again, this is a debate that's not settled yet. Certainly in industry, there's a lot of interest in exploring these sorts of things. Although as far as I can tell, none of the production-ready RDBMSs use ML inside for any components. But again, this is research. You might get more attention from this. Perhaps it'll influence other people to come up with better techniques and lead to more practical systems. So if you're interested in his keynote, go watch his keynote. The video is available, I think, but the slide deck link is over there, down at the bottom of the slide. So what are these areas where heuristics are used that are handcrafted and that what Jeff Dean says are not flexible to the data distributions? Compilers, for scheduling instructions, allocations of registers, parallelization strategies. In networking, there's parameters like TCP window size decisions, parameters for backoffs when you have to do retransmission of packets that failed, data compression schemes. In operating systems, you have process scheduling, buffer cache, insertion replacement, file system prefetching. A lot of these also occur in RDBMSs. Job scheduling systems, when you have a cluster that you're running, you have cluster managers, which tasks or VMs to co-locate on the machines, which tasks to preempt, which tasks to move around. Similarly, in an RDBMS, you have query scheduling and operator scheduling. And even in the hardware level, when you're designing new ASICs, application-specific integrated circuits, you have to decide layouts and select test cases. And he says ML can be useful there too. And of course, anywhere a system has a user configurable parameter where the optimal value may depend on the data inputs, you can use ML with historical data and traces and logs to automatically pick these sorts of parameters. Here's his recipe for how to apply ML to systems. He says, of course, for ML, you need to have a metric that's numeric, that's measurable and optimizable. Then you give this as a loss value or a loss function. And then he says, you need to have a clean interface to integrate the machine learning aspect into these systems. Okay, so you want to be able to do the offline training and the configuration based on historical data. And then you want to have the model that you built to be integrated into the system for use during production. And he says currently they're working on APIs and implementations, make a sequence of choices in some context, get feedback, make all of this work with low overhead, even in distributed setups, and have multiple implementations of common interfaces. Okay, so that was in the context of general computing systems. Let's look at RDBMSs, where in this architecture diagram of an RDBMS that we saw in the first lecture. So going back to the introductory lecture, this is the architecture diagram from the codebook. Where exactly can ML be helpful? One of the most common and one of the most popular usage of ML is for knob tuning and resource management. Like I mentioned, modern RDBMSs have about 100 knobs that you need to tune, and using machine learning and past usage data, what is called telemetry data, can help you automate some of this knob tuning. In the cloud native RDBMS setting, you also want to do resource management, when to free up resources, when to ask for more resources. Trying to automate all of that is possible with machine learning. Now, a lot of this telemetry data is currently in the hands of database companies and cloud providers. It's not available that much outside of academia. And so one of the tussle points right now is how can many of these claims that companies are making about usage of ML in this context be verified and vetted? How can it be reproducible if they're not going to release these logs? And there's a lot of conversations around that. Sigmod and Reality that I saw. And some of these companies like Microsoft are considering releasing logs. Google has also been considering releasing log data from cloud usage. And these logs include things like telemetry, like machine utilization, processor, memory, disk, and so on for different queries, for different schemas, and different data distributions. But it's also been studied in academic research for a long time. A bunch of faculty have been studying this both in the US, in Germany, in China, and a bunch of other areas. Second major area where ML can help an RDBMS is query interfaces. We all know that SQL is the language that most RDBMSs speak. However, on top of that, you can build web frontends, application frontends, like business intelligence dashboards. Increasingly, people are interested in natural language interfaces. And think of, for example, marketing teams or sales teams in enterprise companies. They may not have a CS background. They may not know SQL. And so they still want to ask questions about customer behavior, purchase behavior, ad behavior. If we can allow them to express these sorts of queries in natural language, then we can use ML techniques, specifically natural language processing techniques, to convert those English language statements to SQL. And that's a very hard problem. And people have been studying this for almost 3 decades now, both in the database community and in the AI community. And the state of the art, of course, as you can expect, is deep learning based. And they're using modern transformer methods from the NLP world to convert natural language strings using the database schema, using some other information into a valid SQL query. The state of the art is still very poor. It doesn't work in production ready environments just yet, but it is research. So you make incremental progress the way you can. Another area is buffer management. There's a bunch of learned caching and scheduling policies that people have studied. We will look at this, some examples over here. Recollect that these policies affect efficiency. Access methods, we saw index structures, we saw file layouts. Turns out that you can actually design better index methods and file layouts if you use machine learning methods instead of hand-designed data structures. And last, another challenging area is query processing and optimization. There's a lot of heuristics throughout this. Recollect that query optimization is a very hard problem because of the space of plans being so large and because of all the rule-based heuristics that optimizers have used so far. Like for example, join order enumeration, we've talked about it, left deep, right deep, bushy tree. Different orderings might be optimal in different data distributions and schemas and hardware contexts. Machine learning can help you figure out these sorts of things automatically. Let's dive into each one of these in a bit more detail. Modern RDBMSs have hundreds of config parameters. These config parameters, unfortunately, are not just going to be a set of numbers. They could be continuous, they could be discrete, and they could be conditional. And they can affect latency of the query in very non-monotonic ways. You might think that if you keep increasing a parameter, the performance might keep improving, but then eventually it might drop. Like take, for example, degree of parallelism. If it's too low, you're not utilizing the hardware well. So your computations will take too long. If it's too high, you might end up with contention. Too many threads and a lot of swaps and process swaps leading to a lot of overhead. So somewhere in between is the sweet spot. ML can help find such sweet spots. Okay, so these optimal settings are highly dependent on schema properties, the instance values, the hardware that you're utilizing, availability of auxiliary data structures like indexes, workload properties of the queries. Is it read-write? Is it read mostly? Does it involve a lot of joins? Does it involve a lot of aggregates? So it's a very complex problem, and it's impossible for database administrators to keep up with this and keep delivering optimal knobs efficiently over time. And in the cloud setting, it becomes even more complicated because system or hardware configuration can evolve quickly. And this is where ML can help. The main reason is it's flexible and adaptable, and it can be more accurate. Okay, so you can adapt instantly to changes in the query workloads. You can adapt to flexibility. You can adapt to changes in the hardware configs. And then the target can be flexible. You can configure different loss functions. You can do optimize for latency or optimize for resource utilization, optimize for cost. You can explore different kinds of models with modern machine learning methods that allow you to satisfy different kinds of resource constraints. And of course, because ML is also based on historical data, it's kind of emulating what a DBA does. Like what does a DBA do? They look at historical data and usage and consumption of resources and then try to model it. That's what is being automated with ML. And the buzzword, the industry buzzword you might hear is autonomous DBMSs or self-driving DBMSs. The autonomous word has been around for 20 years now. The self-driving came about more in the last 5 years or so. And that's a term that you get from self-driving cars and self-driving vehicles that people have been using. Interestingly, when I went to an industry conference a couple of years ago, I had lunch with a couple of data analysts and data engineers and DBAs. One of the DBAs told me that he's actually quitting his job and switching over to a developer job because he's worried that DBA jobs are going to be automated. He thinks that all these autonomous DBMS approaches will totally obviate the need to have a DBA, and they will just have algorithms do their work instead. Fear is probably not unfounded, but it's not yet at the stage where you can completely say the entire DBA is removed for everything. It's much more complicated than that. Some examples of research papers that look at the space. So this is a paper from Professor Andy Pavlov's group in Carnegie Mellon. They have this system that has a pipeline where they basically try to use machine learning methods to achieve better throughput for transaction queries. So it's the TPC benchmark queries. You can have a look at the paper if you're interested. The link is down there. Moving on, I mentioned natural language interfaces. And like I said, for sales teams or marketing teams, SQL is just too hard. There's just so many clauses, and it's just very weird to construct a SQL query for lay users. And of course, you take entire courses on just learning SQL, like say 132A, or in the B school, they have courses teaching SQL entirely. But regular people who have not done computer science or B-school degrees or analytics degrees will find it really hard to learn SQL because it is a programming language. Even though it sounds like English, it's kind of in between English and a programming language. And so the goal with NLIs is to just do with full English. They will just ask a query in regular natural language. Like, for example, they could ask a query like, how many customers bought this product, these many values of this product in a particular state. Converting that English sentence into an SQL query is the job of the natural language interface. Okay, so this way, relational databases can be accessed by a lot more people than just SQL users. Increasingly, relational natural language interfaces are seeing adoption in some enterprise settings, especially because sales and marketing people want to ask questions. But these are very simple queries, like one table or few predicates, not too complicated joins or aggregates. It's very hard to convert an English language sentence into an SQL query. People are also trying out conversational style interactions where you can pose a query, the system gets something wrong, you ask the user to correct it, and then interactively do a chatbot style exploration. Okay, so natural language processing is inherently an AI task, and so you have to use machine learning there, and the state of the art in natural language processing is deep learning based. Okay, so there are models called transformers that are the state of the art. These are really large deep learning networks that allow you to extract semantics from the text automatically based on historical text data that they have been trained on. Previously, people did parsing-based and rule-based approaches. They just turned out to be too brittle. The accuracy was too poor to be practical. However, even with the modern deep learning methods, this is a very, very challenging problem. Inferring both the structure of the SQL query, all the clauses and the tables and the schemas, and the literals, like the values of the predicates, it's extremely hard. Many of the standard benchmarks today, like the spider benchmark from the NLP community, actually totally ignores the literals. So it's not entirely useful. You might get some structure on a few table joins, but if you don't have the values of your where predicates, what's the point? The query is not going to be correct. So as far as I know, there is no robust open domain commercial system for NLIs today that will work out of the box in any domain you want, like finance, retail, telecom, and so on. Certain companies, like say from financial companies, they have a domain-specific system for what is called natural language translation, where the scope is much smaller. They only target the schemas that they already have and they already know. You already know that conversational assistants like Alexa, Siri, Cortana, they also allow you to ask natural language queries, factual queries. Like you can ask Alexa, how many restaurants are there, say Italian restaurants are there in this neighborhood. That is going to be converted under the covers into a query over a structured knowledge graph. That's basically a relational database. And so Alexa has to understand the natural language and convert it into a structured query. But that is over databases whose schemas are fixed and whose schemas are known to Alexa's processing system. Open domain means the schema might be given by the user on the fly. And that is not possible with these sorts of systems. You cannot use Alexa to query your, say, customer database. That's not possible. You can only query the databases that Alexa has access to internally. So people have been struggling to build natural language interfaces from both the AI community and from the database community, and the state of the art is getting better and better, but it's still nowhere near production quality. Here's a more recent paper on natural language interfaces. There's a lot of groups in academia in the US, in Germany, in China, in multiple other countries that are actually studying this problem. Companies, some of the database companies have looked at this, but many of them are just not very interested in this because it requires really advanced machine learning and natural language processing knowledge. Again, if you're interested in this, go check out this paper, follow the references there to see the history of work in this space and the state of the art. Okay, moving on to scheduling and caching. So we're now talking about the guts of the system in between the language and the storage. So here, notice that you have buffer replacement policies that we talked about, LRU, MRU, clock, and so on. These are all heuristically designed policies. They do not exploit query distributions or data distributions. And so they might be leaving a lot of improvements for runtime on the table. And so why would ML help here? Because ML takes into account the underlying data distributions and the workload distributions and the access behavior of queries. can potentially reduce runtimes and reduce the wastage of memory and storage for different workloads. And in this context, people have learned schedulers and learned cache replacement schemes. Learned schedulers allow you to load balance computations over workers better compared to existing heuristic approaches. And this can reduce worker idle times to improve resource utilization and or reduce overall query latency. Learned cache replacement or buffer replacement allows you to retain pages better than what a handcrafted heuristic like the clock algorithm would do. It can do eviction decisions better based on historical access patterns and can potentially improve your cache hits and reduce latency further. Some examples of recent research, again, all of this is cutting edge research is from the last year or two for usage of machine learning in the context of a scheduler. So that's the first paper over there, CHDB. This is a group from MIT that's actually working on rebuilding several components of an RDBMS using machine learning. And here is this Professor Mohammad Alizadeh, Professor Tim Kraska. They are actually working on learned schedulers and other data structures. The one at the bottom over there is basically how do you cache data across different tiers of a storage hierarchy. They use a machine learning method called boosted decision tree to actually figure this out automatically. And that turns out that improves your cache hits more than handcrafted heuristics. Moving on, we talked about access methods. Now we are getting into the implementation of relational operators itself. And here the idea is that if you don't utilize the query properties and the system resources well, you might be losing some performance gains that you might get. These sort of things include the layout of the data. So it's memory and storage and runtime, all of them will be affected. And by tailoring them to the query and the database instance distributions, you can wring out more performance from your hardware. Why would ML help here? Well, if you can model the underlying distribution of the joint distribution of the data set itself, then potentially you can reduce resource consumption by either approximating or learning the distribution of the data itself. This can help reduce resources depending on the target queries and the use cases. It can reduce storage footprints, memory consumption, and so on. And two prominent examples in this context is what are called learned index structures. These are basically indexed data structures that are not handcrafted data structures like your B+ tree or your hash index, but rather they are learned data structures. So you throw in a machine learning model, in comes your search key, out comes your location on the file. That's sort of a machine learning model. Turns out that these sorts of learned models for indexing can reduce your storage and memory footprint of the index. And we are talking orders of magnitude, like 10x to 100x reduction in the memory footprint. The B+ tree index is a big bloated data structure. It doesn't tailor itself to the underlying distribution. The basic idea here is that if you tailor yourself to the underlying distribution, you can construct a more succinct data structure, which is an ML model. Turns out it can also help reduce query latency as another benefit in some situations. Compression formats, again, when you're laying out data on file, if you're using the data distribution to come up with compression schemes that reduce the number of bytes, then you reduce the storage footprint. You also reduce the file I/O time to get the data from disk to memory. A lot of compression algorithms have been studied, but if you use machine learning in this context, you might find configurations that handcrafted heuristics may not explore. As examples, here the paper case for learned index structures paper is actually one of the ones that I mentioned, where you replace a B+ tree with a recursive, what's called recursive model index. And that turns out to be much, much smaller than a B+ tree. And turns out that Microsoft was interested in this. They went ahead and implemented an extension to this called Alex that allows you to build a machine learning model-based index that can respond to updates in the data. One of the challenges with learned indexes is one, they cannot tailor themselves to adaptive or changing data distributions automatically. You have to do a machine learning process in the middle. That's a waste of time for query latency. And so adaptive learned index is built so that inserts and deletes and updates can also be possible with the learned index. People have also extended this to multidimensional indexes, things like spatial indexes like R trees. Turns out that they are not very adaptive to data distributions, but using machine learning methods, they are. And in fact, here they are using very simple machine learning methods called piecewise linear regression models that have been around for more than half a century. We're not talking deep learning. We're talking simple linear regression and logistic regression and decision trees and so on. However, deep learning is also being used for a lot of other things. So for example, the paper at the bottom talks about data compression schemes using recurrent neural networks, which is a classic deep learning method. Moving on, query optimization and query processing are also getting modified by the use of machine learning. In particular, we talked about access methods. Turns out that the operator implementations that we saw in this class can also be revisited to take advantage of the data distributions. And this can help improve predictability, it can help improve runtime. What do you mean by operator implementations? All the hash joins and the sort merge joins that we saw can be thrown out and replaced with a machine learning method. Why would this help? Well, turns out that if you approximate or underlying data distribution, you can potentially improve runtimes and or improve accuracy. And so people have considered learned sorting, learned joins, learned query plans. So learned sorting, for example, in the external merge sort that we saw, the runtime is independent of the distribution of values in your file. Okay, so unfortunately, the merge sort doesn't account for, say, if the value is already pre-sorted, it doesn't change much. Your cost is going to be basically the same. You will just be unnecessarily resorting already sorted data. Machine learning can tell you how close the data distribution is to being already sorted. And so now you can do a learning-based sort procedure that can reduce your sort time. Similarly, for joins, if you want to figure out the distributions of the joining attributes, where the records are, you can reduce the lookup cost for hashing and or sorting. So learning-based joins can reduce your latency compared to the hash join or the sort merge join that we saw. Now, these are kind of complicated implementations. So as of today, I don't know any system that actually uses these sorts of things, but it's all in research stage right now. And the rationale for using them is probably going to take a lot more work. Last one is query plans. Sometimes the query plans that RDBMSs produce after you do your physical plan enumeration and costing and you pick a plan, predicting the runtime of that is a hard challenge, part of which is because of cardinality estimation. Turns out that if you can learn query plans, you can actually use machine learning to predict the runtimes of a query. Why is that useful? Well, if you can tell a user upfront what the runtime of a query is going to be, they can do other things concurrently. Like they can go for a lunch or coffee break or whatever. And in the cloud, if you know the runtime, you can provision for resources better. So here's a couple of illustrative papers. Again, SageDB we saw earlier for the Learn Scheduler. Here they're showing a learn sorting procedure. And you can see that the learn sorting procedure actually has a higher sorting rate than even radix sort, which is known to be a state-of-the-art sorting algorithm, and almost 2x, 3x higher sorting rate. In terms of runtime, its latency is comparable to the radix sort and significantly better than, say, quicksort. On the right, you have this deep learning-based architectures for performance prediction. So if you have different components of a query, you want to predict the latency. Here you're using machine learning methods to predict the time of the operator executions and the plan executions. Moving on, now that we've talked about access methods and operator implementations, next thing obviously is optimization. And I mentioned during the query optimizations topic that there's a lot of heuristics that go into RDBMSs to make the optimization problem tractable. There's join orders. You're not going to enumerate all join orders. And so typically some rule-based heuristics are used. There's plan selection, where you have to figure out which physical operator to use where. And then there's cardinality estimation, which helps you decide, again, between operators and resource allocation. And so machine learning can potentially help here because it can approximate the underlying data distribution again. And so it can potentially reduce runtimes for the final plan that is produced. And two specific areas where this has been shown to be promising is learning the join orders. So given a particular complex query over the database, if you want to figure out what is the order in which you want to do the join, people have built deep reinforcement learning-based techniques that allow you to use distribution information about the join attributes to figure out which order is better. And so this can kind of improve latency compared to handcrafted rule-based heuristics for join order enumeration. And then there's plan rewrites. Turns out that some of the algebraic rewrites that we saw, all the equivalences, the relational equivalences, they were all handcrafted based on our understanding of relational algebra. But it turns out if you give enough training data and train over enough lot of historical data, some of these machine learning methods can actually learn to rewrite plans as well. Now, it's nowhere near the sophistication of handwritten rewrite rules for relational DBMSs, but there has been some initial work that has shown promise here. And one of that is the NEO system, again from the MIT group that I mentioned. And here, basically, they're showing that given a query and given a workload information, you can train a model that actually produces a plan and rewrites the plan automatically. And they show that it produces performance comparable to commercial systems like SQL Server and Oracle on benchmark queries like TPCH. Granted, here the number of joins are not particularly high and the queries may not be as complex as many real-world queries, but this is still early stage research. And so they have just demonstrated some feasibility in some contexts. One of the key innovative ideas in this kind of work is the use of sophisticated deep learning methods for plan enumeration and plan modification. In particular, they're using these form of deep learning called tree convolutional networks. Okay, so if you want to understand machine learning for systems and relational DBMSs these days, you better go and take a deep learning course, because deep learning is starting to influence a lot of heuristics that people have in systems, throw that out and then replace that with new methods. One of the benefits of using deep learning in this context is handcrafted feature extraction goes down. If you were to use trees or linear models or statistical methods or SVMs or something like that, you have to do a lot of handcrafted feature extraction to convert these complex objects like query plans and query workloads. With deep learning, that sort of handcrafted extraction goes down. You do more learned automatic feature extraction using things like tree convolutions. Similarly, people are also using reinforcement learning to optimize join orders. And there's a paper link that I've given there if you're curious. Reinforcement learning is a paradigm of machine learning that goes beyond just supervised or unsupervised or semi-supervised learning, where you have an agent interacting with the environment, and the agent is a software agent. It gets rewards from the environment, and then it updates what is called as policies based on the rewards to interact with the environment. And in this context of learning to optimize join queries, they're basically saying, while the query is executing, you can learn more about the join order results and then re-optimize on the fly. So it's kind of adaptive. So that's a wrap on a tour of where exactly in the RDBMS stack that machine learning and particularly deep learning these days are being studied so that you can improve things. ML for knob tuning and resource management is one of the most well-established and commonly agreed upon areas where people are using machine learning methods, typically tree-based methods, SVMs, statistical methods, or also deep learning methods for knob tuning and reducing the amount of grunt work for DBAs. Also in the cloud setting, automating resource management. Then natural language interfaces, long-standing research question, still no end in sight for converting natural language sentences into SQL automatically with high accuracy. People are using state-of-the-art deep learning methods from natural language processing there. Caching and scheduling, we saw a bunch of heuristics, algorithms. You can use historical data and machine learning to improve query latency, to improve resource utilization there. And likewise, the guts of the RDBMS, access methods, query optimization, query processing, and operator implementation. People are revisiting all of that to take advantage of the distribution of the data, the query workload, and all of that, and automatically learn better schemes than the handcrafted heuristics and the handcrafted algorithms that we saw in the particular topic in this class. Now, all of this is in the context of systems aspects of relational DBMSs. Apart from this, there are other areas of databases and data systems where machine learning has been used for a long time. Data integration and data cleaning, for example, these are areas where you will study in a graduate database class 232 or something like that. When people have to unify two companies' databases, they have to integrate and resolve the schemas. When you have dirty data from user inputs or sensor readings or something, you have to make sure the values are updated. That's called data cleaning. In those sort of settings over the last 2 decades, people have kind of come to a consensus that machine learning is inevitable. You will have to use machine learning and human in the loop style methods for data cleaning and data integration. But now in the context of relational DBMS implementations itself, people are starting to visit ML methods and revisit ML methods to understand if you can improve the different components of an RDBMS itself using machine learning. By no means is this a settled debate. It only started in the last few years, and it's probably going to take another decade of work to understand if a machine learning based system components can actually benefit an RDBMS in production settings while giving, say, significant gains in latency or costs for users, but not leading to other issues like unreliability, unpredictability, errors, and whatnot. And for you as a person interested in databases, now it seems like if you want to understand the state of the art in machine learning, state of the art in database technology, you better learn machine learning as well, and in particular deep learning as well, because a lot of the research in this space of different system components, of interfaces, and so on, are applying machine learning and deep learning. Okay, so on top of this, the hardware is also evolving. Like I said, people are coming up with accelerators. There's work on integrating database physical implementations with GPUs and FPGAs. And now we also saw Cloud 3.0. As serverless and resource disaggregation increases, people are re-architecting the physical layer and the runtime and the execution and the storage of the DBMS stack from scratch for these sorts of regimes. Okay, so as the complexity of the hardware and the software keeps improving, potentially machine learning can help with a lot of resource management and knob tuning and other physical layer decisions. Okay, so whatever you studied in this class is so far has been well established, but who knows how the DBMSs will look a decade into the future. So you better stay informed of the latest research along all aspects of the stack. That's a wrap of this topic. Hopefully it was interesting. If you're curious more, curious about learning more about these topics, issues, feel free to drop a note and then I'll send you more references. We don't have any research on campus here on machine learning for RDBMSs per se, but there are a lot of other groups and companies that are working on this. I'm happy to send you some references if you're interested. Again, to reiterate, this topic is not included in the syllabus for the final exam. Okay, this is just for your curiosity's sake. And last, to reiterate again, so go and fill out the course evaluation forms if you have not already done so. If you have done, thank you. Thank you again for taking 132C. All the best for your future academic and other endeavors in your career. Take care.